All right. Good afternoon, everyone. So last lecture we stopped at the Jpeg compressions. I did not share my screen. Why the interface a bit weird? Okay. So in last lecture we learned about the Jpeg, which means the Jpeg. Okay. Before we proceed, we can have a small recap. In the previous chapter, we learned about DFT, DCT, and DWT. So DFT is the basic of Fourier transform, but we are not using these, specifically DFT in the image processing or video processing, especially for compression method. But rather we use DCT and also DWT. DCT is an sort of improvement of DFT. When we compare between DFT and DCT, the main difference would be DCT would be more computational simpler, which means it did not include the imaginary part, whereby only calculations of real part. So the entire calculation will be simple, will be faster, and etc. So that is the difference between DCT and DFT. And for DWT and DCT, and also in contrast with DFT, DWT would be better instead in terms of the DWT consists of the spatial and also the frequency domain informations. Because when we convert from one domain to another domain, especially from spatial domain to the frequency domain, we actually losing. I mean, not really losing, but actually you're converting everything to another dimension. So we don't really lose the informations, but instead we are convert to another another different dimension and extract different, and present in a different way. So when we convert, DFT and DCT, we actually lost all the spatial domain informations and we only have the frequency domain information. But for the DWT, we actually have both of these information. So that is why the effectiveness of DWT would be better than the DCT and DFT. So DCT is the core for Jpeg, and DWT will be the core of Jpeg 2000. So that is the difference. So in previous chapter, we learned about DFT, DCT, and DWT. So in this chapter, we learn about why we need to do image compressions. So basically two reasons. The first reason is that we have limited storage. The second reason is that we have limited bandwidth. Okay, so I think the same reason is applicable to audio and also to video processing as well. So that is the reason why we want to do compression. And uh, we also learn about lossy and lossless. So lossy is that the information cannot be recovered. We have lossy and lossless. We have lossy and lossless. So for lossy, we actually cannot recover the omitted information, but for lossless, we can. But when we compare between lossy and lossless, we will find that the lossy has a higher compression rate. For example, 45 to 1, 50 to 1 is more than the lossless. Lossless maybe can up to 10 to 1 and etc. Okay, but in another way, the lossless can recover all the informations where you have compressed in the previous algorithm. Okay, so basically Lucy and Lucid is to describe the algorithm instead of the final image. So we're not really describing Jpeg as Lucy or Lucid, but we describe the algorithm to perform the Jpeg compression is Lucy or Lucid. Okay, that would be a minor, the point there is different. So this would be the main step to perform Jpeg compressions, whereby you need to perform DCT, quantization, zigzag ordering, run length encoding, or what we call RLE, and also DPCM, and entropy coding. Okay, so in the subsequent slide, if you not understand, please, for those online, please use the raise hand button, or maybe you can put it in the chat box. But for the, or you turn on the mic as well, okay as well. And for those physical, please let me know if you don't understand. Okay, so this would be the overall, flow of the Jpeg compression. Jpeg compression is an algorithm, and this algorithm consists of all these informations. So first of all, you have the input image. So input image would be usually would be in RGB Even though it is not in RGB, you still can convert to YCBCR. Okay, so after that you convert to YCBCR. The first step is to convert the input image to YCBCR and subsampling to 420. Okay, so the input image would be the original image. Usually it is in RGB color model, and convert to YCBCR. Basically you just you can convert it easily by using MATLAB, and then subsampling to 420. I would explain the 420. I think end of. I'm not sure this chapter or next chapter. Okay. Subsampling, we will learn this later on. I think during the video processing. 420 is that is the factor, is the ratio. You compress the image into different, this is 420. Okay. You compress it into different value. I mean, subsampling into different value. Because human eye is more sensitive to certain channel and not sensitive to certain channel. So that is why those channel that we are not really sensitive, so we try to compress more. And those channel which is more sensitive towards it, so we will try to retain as much as possible. Again, Jpeg compression is meant for human being, which means the image is intended to read or to display or to view by human being and not the machine vision. So that is why we are trying to do everything, and it is based on human perception. Okay, not based on any machine vision perception. Okay, so the first three step is very easy. Just simply convert it to ICBCR and subsampling to 420, and then for each of the component, divide it into 8x8 pixel group. You can actually divide it into 8x8 pixel group or 16x16, but usually in Jpeg the most conventional way is to divide by 8x8 pixel group. By dividing this to 8x8 pixel group, you can have a better compression and also with a shorter time. If you have a larger and larger pixel group, perhaps the compressions time taken required to compress the image will be longer and longer. Okay, so later on, each channel of the image is subdivided into 8x8 pixel group, and if the image is not exactly multiple of 8 pixel in width or height, it is temporarily pad out to that size. The pad out depends on what pad out you want, because we already learned our padding, right? Zero, mirror, and also reflection. So usually we are using zero padding. Okay, most of the time by default you're using zero padding. Okay, so basically the main purpose is because you cannot process the image without the exact number of pixels. You cannot process something empty, which means if let's say you need more pixels here, so you need to add in with the pixel accordingly. You cannot process empty pixel. Okay, so subdivide into 8x8 pixel group and perform block shifting and perform DCT. Basically, block shifting is to minus by 1 to 8 lah. Okay, as I mentioned before, you have a sinusoidal wave, right? So you're actually moving it uh, downwards lah, which is 0, 1 to 7, 1 to 8. Okay, 1 to 8. So in total, you have 2, 5, 6 value lah. Okay, so basically, this is also obey the Naive theorem lah. You know, to make it flip it over downwards there. So every pixel will be minus by 1 to 8. So in that case, you might have negative value in this stage. It's normal. Okay. So DCT, each 8 times 8 pixel group is processed by using DCT, which is much likely the Fourier transform, except all the value are real instead of complex in DCT. So this would be the main difference. All the value are real. Okay. The DCT for an 8 times 8 pixel block this is the equation for DCT to get the coefficient. So the DCT highest energy low frequency term to the upper left column. Upper left column, which means this is the upper left column. This would be the after convert to DCT, the upper left column would be the DC value, and also it is more likely to be low frequency information, and the rest would be high frequency information. Okay, so this is the way after convert to DCT, that is the information you can retrieve from. Okay, the lesser energy high frequency is reallocated into other area, which is this area. Using block, however, has the effect of isolating each block from its neighboring context. This is why Jpeg image looks blocky when the user specifies a high compression ratio. That is because you're actually moving everything, process everything in an 8 times 8 pixel block, 8 times 8 pixel block. And this 8 times 8 pixel block is repeat. I mean, the entire process are not the pixel value. The entire process is repeat to the adjacent another 8 times 8 is repeated until you have the entire image. So that is why since you're processing the image in 8 times 8 pixel block, after you finish processing the image, you would expect that, of course, when you are using very high compression ratio, so you would expect to see a blocky field when you zoom in the image as per the previous image, like the Lena, the eye over there. So you would able to see something like that. That is because the main reason is that the Jpeg is actually processing the image in the 8 times 8 pixel block. Okay, eventually it's using 16 times 16. Basically the block would be, the blocky field would be bigger lah. Okay, that's all. Okay, but nonetheless, it is still remain as a blocky field. So later on, you perform quantization. Quantization is actually just to divide by something else. Like like for example, you have 20, so you divide by 2, you will get 10, right? Okay, something like that. So quantization is a table provided by the Jpeg. So basically, if let's say the table is already fixed. For example, I want to perform 10 to 1, so the table is already there. It will be given. So basically, your input pixel value, all the input pixel value will be divided by using that box. Of course, because you are processing the image in 8 times 8 pixel block, right? The block, the quantization table provided will be in 8 times 8 as well. So basically, you just need to divide the first value of your DCT by the first value of this value from the quantization table, that's all. Okay, so let's say this is 20, this is 10. So after you perform the quantization, you will get 2. Okay, and so on and so forth. So the quantization step in Jpeg compression is aimed to reduce the total number of bits needed for a compressed image. It consists of simply dividing each entry of the frequency space block, which is the DCT coefficient, by an integer followed by rounding up. Of course, whenever you divide, you would get sort of flat value, right? Decimal place of it. So you just need to round off. Okay, because in pixel, we don't really, especially for in the range of 0 to 255, we don't really take flat value. But of course, there would be depends because for those normalized case, which is in the range of 0 to 1. So for sure, you will have floating flat number, okay? So quantization quantized DC coefficient. So this is the quantized DC coefficient, which is represented by using this, okay? So basically, this is the DCT coefficient, this is the quantization table, and this will be your output, okay? Although it is not a must using F, Q, and also F, I don't know this info forward, okay, with this symbol, but of course you have to know, but I believe it is appear in the questions, I mean in the examination, you would be giving, I mean given the this symbol represent what, okay? But anyhow, if you are going to write F U V as your DCT coefficient, then after perform quantization, you are still writing this one, so which means definitely wrong, okay? You should have maybe Q, Z, whatsoever variable, but of course you need to use this symbol to represent the quantized DCT coefficient, okay? So the default value of the quantization table for luminous and chrominous image are listed in the next slide. So the entry of the quantization table tend to have larger value towards the right corner, also towards the lower right corner, and this aim to reduce more high frequency information. So this is the example for luminance and also chrominance. Luminous and chrominance will be different, which means YCBCR, some are luminous channel, some are chrominance channel. For those channel which is human eye not so sensitive in, would be compressed by a larger scale or the quantization number. So this is the example of the luminance quantization table, this one, and this is the for chrominance. So as you can observe, the value towards this end is much more larger. Towards this end would be smaller. Okay, so which means this is 16. This is 16, but this is 99. 100 something else. And when you look in towards this direction, the value would be reducing. The same apply to here. All the value at this end would be quite big, which is 99. But towards this end would be smaller, which is until 17. So this is the quantization table, and this will be provided. So DCT value, so this is your DCT value. This is, let's say this is the luminance quantization table, and this is after the quantization. How to do so? This is actually 512 divided by 16. So you will get this one. Of course, you need to round off. And for those value which is very small, like like -3 divided by 101. So round off, you will get 0. Okay. Basically, because -3 divided by something very big, you will get 0 point dot 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 something else, right? So those will be round off to become 0. Okay. Yeah. So you can try to calculate a bit, at least to understand how you get this value. Basically, just divide it by using the quantization table. That's all. And as you can see, for a compression factor which is greater, for example, 45 to 1, 50 to 1, this table, the number will be larger. Why it is being larger? Simple mathematics, 100 divided by 10, you will get something smaller. But when you compare to 10, 100 divided by 100, you will get actually 1, right? So basically, when the value in the denominator is greater, the output value will be smaller, right? So this is the logic. So that is why for those using the higher compression rate, you would expect this table, the value in this table would be greater in their scale. Okay, so if let's say this table, the number in this table remain unchanged, which means all are 1, 1, 1, 1, 1, 1. So what does this mean? Any compression? Any quantization performed there? If everything here is 1, any compression? No. So that is how is it? But of course, normally you won't do something like that, like you're taking a bus, and then after taking a bus, after one trip, you're back to your original spot. This is something quite stupid. But but nonetheless, this is the logic over there. Okay, so if let's say the value here in this table is greater and greater, so which means you have a higher and higher compression rate. Okay, so far can understand. So we have already done this input image, convert to YCBCR, subsampling to 420 using 8x8 pixel group, and then block shifting. Block shifting is to just minus by 128. Okay, so and then perform DCT. After that, quantization. So after quantization, you will get a table like this one. This is the table after you get the quantization. Okay, which means this part is actually this one. Okay, can you recognize this symbol? So it is at this part. So after quantization, and also I do remark that Jpeg supply the quantization table. So please, you don't need to memorize the table. So after that, you will get something like this. As I mentioned before, the value here is the DC value, and the rest is the AC value. So the way we process DC value and AC value is different. Okay, so let us proceed. So in this flow, we have different DC coefficient and AC coefficient. For AC coefficient, we are actually processing using the zigzag ordering, and then followed by RLE. But for DC coefficient, we are using DPCM. Okay, so far can follow. At this point would be a bit complex. At this point, over will be a bit complex. So let me repeat. So after you perform the quantization, you will get this table. So from this table, the first value will be the DC value, and the rest will be the AC value. Okay. So the way to process DC value and AC value is different. Okay. So let's look at this one. We are using DPCM to process the DC value and using the zigzag and followed by RLE to process the AC value. So first of all, we learn about the DPCM first. DPCM is actually referring to differential pulse code modulation for DC value only. So the DC coefficient are coded separately from AC coefficient. In practical, actually the DC value will be extracted from each block. We have different block, like, so for each block we have only one DC value. So actually in practical, we actually extracting all these block and then we combine together to process it separately. Okay, so each this bullet point, each A block has only one DC, and the DC coefficient from different image block are coded together. So if the DC coefficient for the first 5 block is this, and this, followed by this one, then the DPCM would be produced as this one. Do you know how it is being produced? Can you see the patterns? I think in Form 5 or in maths, they like to ask you all to identify the pattern like APAR. Is it something like that? I think there is APAR in Form 5, right? Something like that, right? To ask you to identify the patterns of the a series of numbers. So that is how we use that. Recently, I encountered a question from students. He thinks that we are, after we grow up, we don't really use all those standard deviation, all those differentiation. It's true lah. If you are, I would say it's true. If you are not doing anything, you are just buying Starbucks, it's okay lah. You don't need to calculate standard deviation for that one. But if you are going to do engineering, I believe start from the second year, you are trying to use a lot of rate of change. Whenever you deal with rate of change, you are actually dealing with the differentiation. Okay, differentiation is the small rate of change, so we call it differentiation. Integration is the inverse of it. So yeah, in engineering, very important for those. Okay, so let's back to here. 155 negative 6. Actually, this code, all these code are being coded as this one. So how is being coded? We just extract the first value. So 150 is the first value, right? Followed by the second value, which is 155. So basically, how we get 5 is actually 155 minus by 150. So you will get 5. Okay, not common. 5. So later on, from this value, you need to calculate the next one. So the difference between 149 minus by 155, you will get -6, right? So followed by -6. And again, continue. You add on 5 as add on 3, which is you don't really put in the plus sign, but just positive. And then followed by -8. Okay. So basically, yeah, this value, this value are actually the summation value from the previous one. So which means 150 plus positive 5, you will get 155. 155 plus -6. Actually, the theory is plus plus something else. So that is why you have negative signs here. Okay. So which means 150 plus 5. So you will get 155. And then 155 plus -6. You will get 149. And 149 plus 3, you will get 152. And 152 plus -8, you will get 144. Can you get the idea? Okay, so this is how actually we are, because when you want to, in computer science, if you want to code something longer, which means 150, in order to display 150, and to display 1, they are using different bit. Because the smaller the value it is, I mean, one place, two place, or I mean 1 digit, 2 digit, or 3 digit, the bit required to display this value or to carry this information is different. The longer the value, the larger the decimal place, the larger the bit required. Okay, so that is why it try to reduce it to become single digit. Okay, so that is why 150, you have to take this because this is the value, the initial value. Okay, so later on followed by 5 and followed by 6 and so on and so forth. Okay, so DPCM code are expected to generally have small magnitude and variance, which is beneficial for the next entropy coding step. Basically, the magnitude, I mean, the differences between the first and the subsequent ones would be not that high, because low, because DC is highly about low frequency information, and the low frequency information across the entire image would be, I wouldn't say constant, but would be a bit stable. Okay, of course, if your input image is corrupted by noise, it's different case. But most of the cases, the DC value will be a bit stable. So eventually, the plus and minus would be around up to 2 digit maybe. Wouldn't be up to 3 digit. 3 digit is a very noisy already. Okay. So far, is it okay for DPCM? Okay, let us go for AC, zigzag ordering and RLE. This is a bit interesting for zigzag ordering. No, zigzag ordering, zigzag is zigzag, right? This is zigzag, okay? So zigzag ordering is exactly doing something like this one. So the quantized DCT coefficient are then zigzag scan, transforming the 8x8 matrix into 64 vector. The most image block tend to have high frequency component, which are zero out by the quantization step. This is explained by this one. Because most of the high frequency information, as you can observe, only few number towards this side has a positive, as a digit, okay? But the rest of it over this side, I mean the bottom right side would be 0, okay? So the zigzag order therefore has a good chance to concatenating or link together the long run of 0. This is actually how zigzag quantization being performed. The first value is the DC value, and then the zigzag performed in such a way. Follow the arrow. Okay. Please, this is the default zigzag patterns in examination. Please do not write in the other way around. The whole answer will be wrong. Okay. Please, this is the default by Jpeg. Eventually, you ask me why I can only say this is the default algorithm proposed by Jpeg. Okay. So basically, towards downward and back upwards, I think it's the same. I mean, it won't affect a lot the way the algorithm process. Just that the value obtained would be different. That is because whenever this would be the sequential would be very important for you to decode the image later on. Okay, so that is why if people are going this way and you're going another way around, although the compression rate would be the same, but later on when you display the image would be upside down, something like that. Okay, so make sure you start from the right hand side first. So for example, the 8x8 quantized DCT coefficient in the block below will be 32. So we have this example. So start by 32, 6, and so on. So since we are going zigzag, so the value would be like this way. Yeah, this one to take already. So the value would be something like this, and so on. Okay, so the zigzag value would be 32, followed by 6, followed by -1, -1, 0, -1, and 3, 0, -1, 3, 2, 0, 1, and dot 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 until another 0. You don't need to write all the 0 out. If and only if the rest of it are 0. So you can use these 3 dots to represent. Okay. If let's say you have maybe 32 and then followed by 9, 0, and then followed by 1, and then followed by all 0. So you have to write 32, 9, 0 over here, and then followed by 1, and then 0, and then dot dot dot, only 0. In this part, you cannot use dot 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 because dot 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 is referring until the end. Okay. So the first value of the string is referred to DC value. Again, the 32 is referred to DC value, while the remaining 63 value are referred as AC value. So RLE, the RLE is actually encoding is then applied to 64 vector by replacing the value by a pair of run length and value for each run of 0 in the AC coefficient, where run length is the number of 0 to skip and value is the next non-zero value. A special pair of 0, 0. This is to remark the end of block, which means the last value here, 0, 0, is referring the end of block. So usually we will have this 0, 0 to refer to the end of block. Okay. If you without this one, for sure it's not complete. Okay. The previous example, this is what we obtained. Okay. Now we will learn how to get this one. In the previous example, still can recap. This is the value obtained in the previous example. So after the run length RLE, you will get something like this one. How do we get this one? By this one. So this is the value, AC value. I mean, not the AC and DC because the first one is the DC, the subsequent is AC. So this is the value we get from the previous quantized DCT coefficients. So how we actually do this is like this one. The first value here shows the number of 0 to skip. For the first one, we only look into this one. Do we have any 0 between 32 and 6? No, right? So you have 0. So the next value is 6. So we put 6 over here. The next one, let me remove this. Let me remove this first. The next one, 6 and -1. Do we have any 0 between 6 and -1? No, right? So 0. The next value will be -1. Okay. So when we continue this, so any 0 between -1 and -1? No. So 0. And the next value will be -1. Okay. So the next one would be this one. Any 0 between -1 and -1? 1, right? So we have 1. 1 is referring to number of 0. Okay. And the next value is 0. So we continue for this set of data. So do we have any 0 between this one and this one? Yes, 3, 1, 2, 3, right? So this is 3. And then the next value is -1. Okay, and so on for the next one. 2 value, 2 0 here, so 2, 1, so 1. And then this one we directly put the 0, 0, which means this is the end of block already. Okay, so this is actually how we obtain this one. Is it clear? Okay. So this is how we done the AC and DC coefficient. So this is the intermediate notation, which is something like this one. Okay, and then we use the Hoffman, Jpeg supply the Hoffman coding table or arithmetic code. So by using the coding table, you will actually get all these bits value 0, 1, 0, 1, 0, 1. Okay. So any questions for the previous step until zigzag and RLE? Any questions? No. Okay. So entropy coding is to convert the run length here, all this value into 1010 bit. Okay. So basically the entropy value would be proceed by using the following 8 times 8 pixel block. Entropy coding for DC coefficient. The DC coefficient are differentially coded as size and value. Size is the size of this specific value, and the value is the value. Because in computer science, we don't have others number, we only have 1 and 0, which is high and low bit only. Okay, so in order to code this, we will need to declare the size, for example, 4. For example, the value of 4. You need to know the size to hold the value of you need to know the value for 4, for example 1011, and the size to hold this value, another one. Okay, so basically this is how entropy coding doing. This is what entropy coding doing. Okay, the code for size can be derived from the Hoffman table for DC coefficient size field. If a DC coefficient is 40, so and the previous coefficient is 48, so the differential is 8. So this is DC value, right? So DC value we are using the DPCM, which means we are getting the difference between, for example, the previous is 48, the next is 40. So you have 48 followed by -8 and so on and so forth. Okay. So let's say let assume the current value is -8. It's 40 actually. 40 because you compare with the previous one is 48, let's say. So you will get -8, right? So -8 is the value that you need to compress. Okay. Not compress, it's the value that you need to perform the entropy coding. Okay. So -8, the value is this one. How you actually get this one? You are getting from the size and value table. So this is -8. This table will be given by the Jpeg Hoffman coding table. So from this table, you will need to find the value here. Because the current value is -8, right? So from this table, in the value column, you need to get -8 and get the code, which is this one. Okay, so which means -8 is equivalent to 10111, and the size is 4. Okay, so as I mentioned, the coding should be combined with size followed by the value. Since the value is 0111, so the size is 4. So next to do is to get the size, the code for size. So this is another table. The size for 4 is 101. So you combine with 101, so you will get 1010111. This is the final value. So this is how you get 1010111. Do you understand? Okay, let me recap. In order to perform the entropy coding, first of all, you need to complete the DPCM. So since we are doing for DC first, followed by AC, and for DC value, after the DPCM, let's say the first value is 48, the second value or the current value you want to perform the entropy coding is 40. So based on DPCM, 48 minus 40, you were able to get -8, right? -8. So which means the DPCM is 48, -8, Okay, we only concept of this one. Let's say this is the example. So for -8, you need to refer to this table provided by Hoffman coding, which is a size and value table. You need to find your value, which is -8. After you get -8, get your code number. So basically, to perform the Hoffman coding entropy, the first set is the size. The second set is the value. So since the value of -8 is 0111, so 0111. So this is your value. but you need to get the size. This is the size, okay, size column. And you look into the size table, Hoffman coding for DCT component size field. So number 4, right? I mean 4, the size is 4, right? So you get the code 101. So 101. So this is the final value for your Hoffman coding -8. Okay. So this is how you get this one 101, 0, 101. So 101, the value representing the -8 in the size and value table is 0, 101. And 101, find the size of 4 in Hoffman coding and you get the value 4 is actually 101. Okay. So this is the value for DC. And we continue this for all the AC. Okay. So so far, is it okay for DC value? Okay. If not okay, let me know. Because it's quite difficult for you to follow later on. So entropy coding for AC value coefficients. So now we are explaining the AC coefficient. So AC coefficient are coded in S1, S2, and S2 pair. So this is the different S1 and S2 pair. So S1 is the run length size. Run length size is the length of the consecutive zero value, which is the 0. Because for AC value, you have two value, right? For example, 0, 1, for example, 0, 6. Recall back this one. This is your AC value, because DC is different. Okay. This is referring to AC value. The first one value is 0 followed by negative. First value is 6 followed by -1 and so on and so forth. So the size, the number of the bit needed to code the next non-zero AC coefficient to be A dash your A value. Okay. And this one is referring to end of block, which is 0, 0. Okay, when you need to put this one for the last block. So S2 value, the value of the AC coefficient refer to size and value table. So this is the run length and size and table for the AC coefficient. Actually, sometimes it's quite difficult for you to understand. We go into example, then it will be easier. Consider encoding the AC value. So this is the AC value. This is the example. So 40 is your DC, and then followed by this way until the last. Okay. So from here, you will get the zigzag order will be this one. 10, 12, 10, 1, -7, 2, 0, -4, and 56, 0. Okay, 56, 0 will be this here. So for 12, after the RLE, the 12 will be this value, and the obtained code is this one. How we actually get this one? First of all, you get the yellow color 1100, the code for 12 from the size and value table. So first of all, you need to get the 12 here, which is this value. Okay, so 12 is actually equivalent to 1100, which is this one. And then later on, this is 4, right? So you need to look into this one. This is 4. This 4 is different from the DC value because this one you need to consider the number of 0. Do you still remember the number of 0? For example, 0, 12. Do you still remember this one? So this one have to consider this one. So that is why in this table you have 0/4, which means the size is 4 and the run length of the 0 is 0, which means no gap between this and the previous number. If you have 1, 1, which means the size is 1, but there is a 1, 0 gap between that. And if this is let's say 4, 4, so you would have the size, the current size is 4, but you have 4, 0 between you and the previous number. Okay, so you have to refer to the correct table. So since this is 4, so since you have 0 value, I mean 0 gap here, because how do we know you have 0? It's because 40 and 12, there is no 0 between there. So that you have a 0/4. Okay. 4 is obtained from this table. So 0/4, the value is 1011. So that is why when you combine with this value obtained from the size and value table, 1011 and 1100, you will get this value. Okay. So is it clear how you get the value? And then for the later step, you just need to repeat. Okay. Might be a bit confused lah for initial. I mean, you have to try this. I always recommend that people to try to check and try to, I mean, do example. It's better than explanation. Mm. So note for AC coefficient, it is good to find the S2 value first. It is good to find the S2 value first. Then from the size and value table, determine the size. Next, determine the number of zero from ILE, and then determine the S1 run line. So which means it's always, I would suggest you all to get this value first. If not, how you know what is the size? If you not yet get 12 value, you won't know what is the size. For example, if you are 3, so the size is 2. So from 2, you need to get return back to your run line how many 0. If you have 0, which means 0/2 lah. So from this table, you will get 0/2. If you have 2 0, so 2/2. So from this table, you get 2/2 and get your number of bit. Okay. So that is the tricks over there lah. I would suggest you all to find the value first and then go for the next, which is the get the size, and then after get the size, determine is there any 0 gap. Okay. So that is how you get for 10, this is the value, and for 1 is the same, and so on and so forth lah. Okay. 0, 1, 1 represent of -4 from size and value table. We look into this one. And the rest, this long code is the 10-bit code from run length size, which is for -2 and 3. 2 and 3, I did not provide here. So 56, 0 is 0, 0, so this is the value. So later on, for all of this, in order to summarize it, the DC value, this is the code. The first AC, second, third, fourth, fifth, and the last one. This is the value. And then you combine this value together, and this is the final coding. Okay. Always remember in computer science, actually, we are not doing that one because this is not the assembly value. Usually, even though next time you work, usually we are doing, especially when dealing with machine. I mean, your algorithm is tend to control the machine. You are usually using C#. Okay, because machine would be better. You don't need to convert lah. Usually we are using C#. Whenever you deal with machine motion, we are using C#. Else you are using C++. Okay, because C++ would be easier to convert to C#, and C# directly can control the machine. Okay, we seldom do write assembly language because that one is quite difficult for us to understand as well. So, but nonetheless, this is this is the language computer understand, which is the bit stream. Okay, so this is how you get this value. Any questions from the Jpeg conversion? No. Again, Jpeg conversion is very important. Okay, please focus on this one. So no question. Okay, so if no question, so let's continue. That's all for the Jpeg compression. Let me give you a small recap. So first of all, you would have your input image, and then you convert your input image into YCBCR. So you perform subassembly 420, and then later on you divide into 8x8 or 16x16, but usually we are using 8x8. So after that, for each of the 8x8 pixel block, you perform the block shifting, which is actually -5128 and then you perform the DCT. After -5128, this would be your value, and then you perform DCT. This would be your DCT called efficient. After that, you perform quantization. This quantization table is provided by Jpeg. After that, you will need to separate it into DC and AC value, whereby the first value is DC and the rest of it is AC value. So for the DC value, you need to perform DPCM. DPCM is easy. How? For example, you have first value 48, second value 40, third value maybe 30, maybe 32. So this is 48 followed by -8, followed by -6, and so on and so forth. Okay, so you that's all for DBCM lah. DBCM stop until here, and then you look into ILE, zigzag and ILE. Zigzag is simple. How? You just need to go on zigzag value. I mean zigzag pattern. And make sure you go into the correct directions, which is start from the right hand side. And then later on, perform ILE. First value is 40. So any value gap between 40 and 12, no, 0. And then later on, any gap, no, 0, 10. Then followed by 0, 1, 0, -7, 1 gap, 1, 2, 2 gap, 2, 4, and so on. No? Oh, no already. Oh, -4, sorry. -4. And then followed by 0, comma 0. Okay, so that is it. Quite simple lah. Okay. Of course, you need to know the patterns over there. That is simple lah. And then later on, intermediate notation, which is this one. These are intermediate notation, and then perform entropy coding. So entropy coding is to code this one into 0 and 1 bit string. So you have for -8, right? So -8, find your table in the size and value table, get the code, for example, this one, and get your size, for example, 101. Okay, so this is the DC value. And for AC value, for each of it, you need to look into the value first. So the value is 12. So for example, 12 is 101. Example only. So you look into the size. For example, the size is 4. So since you have zero gap, so 0/4. Look into this table and get the code. For example, 1111, then 1111, 1111, combine with 11011. This one combined with this one. So this is the value for this set only, and then continue for the next set until you finish off. Okay, so that would be the bit stream showing here. Okay. So Jpeg 2000 compressions. The Jpeg 2000 will be using DWT, but we are not going in depth for Jpeg 2000. Okay. So the Jpeg is under both ISO. ISO is an international organization, like the UNICEF, WHO. It is organization which standardize all the things. Okay, ISO do, if you're all interested, next time when you work as an engineer, you all might venture into ISO. Not really venture into ISO, but actually ISO is regarding the quality control, which means the most common one is ISO 9001, 2015, which is about the QMS, quality management system. Of course, there are a lot more ISO like 45,000, which is about safety, 10 something else, which is about the electricity. Those are ISO lah. ISO is more, if you are interested in standard quality and procedure wise, you may venture into audit, because audit, I mean, quality engineer in all engineering field is very high demand, I would say, but the work is very boring as well, because you are dealing with a lot of documentation. This word, why using this word, this and that, a lot of documentation required. But if you are very meticulous people, great attention to small details, then this is a very good industry for you to venture. All the engineering industry require quality engineer. Okay, but the quality engineer is a bit more on quality control. People work a lot. Okay, but unlike all those product development engineer, you're dealing with product and etc. Okay, um, I think that's all for today. First, we will continue the last few slides next time. Oh, a warm reminder: the next week I will off from office. Next Tuesday we will have online class. Okay, online class. I make sure you don't come. And the lab is online as well. Okay, if you need to use the lab, please let me know earlier. I will let the technician know. Okay, let me know the number of people that you wish to use the lab, and let me know earlier. I will let the technician know. Okay, so next Thursday we don't have class because last Thursday we already replaced the class already. Still remember last week Thursday we have 2 hours class is to replace next week. Okay, so Next week we don't have tutorial as well, but later on we do tutorial because next week is odd week. Okay. So see you all later on 4:30, and bye bye.